Yeah. But anyway, yeah, so let me get started. So, as Antonio said, I'm Nicolás Bernal from Universidad de Nariño in Bogotá, Colombia. And we'll be talking about this series of work that I've been doing in collaboration with several colleagues and friends. So Oscar Zapata from Universidad de Antioquia in Medellín, Fasollah Karim, who's a postdoc in Padova, Juber Perez, he's a postdoc now at Durham, and Yong Shu, who is my PhD student. He's about to finish. He's based in Bonn, actually. Yeah, so we'll be talking about dark matter and the possible connection with black holes, and in particular with primordial black holes. Okay, so let me first start with some motivation. I guess that you guys are super familiar with and convinced about the existence of dark matter. Just let me emphasize a couple of points. So we're kind of sure about the existence of the dark matter. And the important point, what I want to stress, is that there are these several observations of the existence of dark matter. It's actually, so it's a missing gravitational force, and all the observations that we have come from gravity. Another key point that come at very different scales. For instance, scales of galaxies. We have the flat behavior of the rotation curve of galaxies, so a scale of galaxies, so kiloparsecs or so. But we also have some evidence at much higher scales, for instance, the scale of clusters of galaxies, so megaparsecs. We have also the flat behavior of the rotation curve of clusters, but also we have, for instance, this super well-known example of the bullet cluster. So kiloparsec, megaparsec, but also even higher scales. So the biggest scales of the universe, so cosmological scales, when we observe the anisotropies of CMB that have been measured by Planck, for instance. And this, so here I'm showing you a map of the CMB. And these small anisotropies, so 10 to the -4 or so, could be very well explained in the context of the lambda CMB, lambda CDM, sorry, model, where dark matter, and in particular cold dark matter, plays a fundamental role. Okay, so what is the dark matter? We don't know, so we can recast that question in the following way. So we can ask ourselves how dark matter was produced in the early universe. So there are many mechanisms, many possible mechanisms, but I think that by far the most well-known, the most studied mechanism for producing dark matter in the universe, early universe, correspond to the WIMP mechanism, where WIMP correspond to weakly interacting massive particles. And the key point for the WIMP paradigm is that we assume that dark matter reaches chemical equilibrium in the early universe with the standard model plasma. So for instance, here we can assume that we have two dark matter particles, two black dark matter particles, these black dots that annihilate into a couple of visible particles, so E plus E minus, or a couple of quarks, or W plus W minus. So two standard model particles that can annihilate into a couple of standard model particles. So we want this reaction to happen, but also the opposite reaction. So the production of dark matter out of collision of standard model states. So we want these two reactions to happen in the early universe and to happen exactly the same rate. So that's what I mean by kinetic, by chemical equilibrium. So we want the dark matter to be produced and to be annihilate, and these two reactions to happen exactly the same rate. That's the idea of chemical equilibrium. So here, for instance, I'm showing you a plot of the co-moving dark matter number density as a function. So the dark matter in the early universe is in chemical equilibrium. That means that it's tracking the equilibrium density. And at some point, this equilibrium will be broken, and will be broken basically because the universe starts to be too big, too diluted, too cold, and this reaction will fall out of chemical equilibrium. And once the dark matter goes out of equilibrium, it will not track anymore the equilibrium density. You will have like this kind of plateau, meaning that the dark matter freezes out. So that we are able to produce the observed dark matter abundance via the WIMP mechanism. So the WIMP mechanism I was telling you is super, I think it by far is the most studied mechanism for dark matter production. And it's super nice because if dark matter is with a WIMP, it will be kind of possible, or at least in principle, to test it via several different mechanisms. For instance, we could test it via direct detection, indirect detection. We could produce in collider, for instance. So it's a very nice mechanism from the phenomenological point of view. However, there are big problems. And for instance, is that we're already testing the bulk of the parameter space, the natural parameter space of WIMP, and via different detections. For instance, here, just to show you an example that comes from the LZ experiment, so the Large Zeppelin experiment, that, so this corresponds to the latest results released last month, so late July. So for instance, here I'm showing you an exclusion plot of the WIMP nucleon cross section as a function of the dark matter mass, of the WIMP mass. And this thick black line corresponds to the latest results, so the latest exclusion plot. So everything above this line is already ruled out. And it happens that this is like kind of the natural parameter space of the WIMP. So dark matter in the range of GVs or TVs, and couplings of the order of the electroweak scale, right? So I think it's fair to say that WIMP dark matter is under tension, under a big tension, because of the non-observation in experiments, in particular indirect detection, and colliders. However, it's not a problem per se, because even if we love WIMPs, it's not the only possible production mechanism in the early universe. So one possibility is not study WIMPs, but FIMs, where F corresponds to feebly. So FIMs correspond to feebly interacting massive particles. And the idea is very simple. For instance, I'm showing you here the same Boltzmann equation that one has to solve if you want to track dark matter abundance in the early universe. However, even if technically it's very similar, philosophically it's very different. Because if WIMPs, the idea was to have chemical equilibrium, meaning that the annihilation and production happen at the same rate. For the FIMs, we want to avoid such an equilibrium. So actually, in the early universe, we want dark matter to be produced out of the standard model particles, but we don't want them to be to annihilate. So we want, even if these two reactions can happen, we don't want them to occur at the same rate. So we really want to avoid chemical equilibrium. And for instance, here I'm showing the evolution of the dark matter abundance. So again, the gray dashed line corresponds to the equilibrium density. And these three lines correspond to possible dark matter evolution. So I'm saying that dark matter is basically being created out of the standard model plasma. So its relic abundance slowly increases. And at some point, dark matter will freeze in, meaning that it will reach a plateau that will correspond to the observed dark matter abundance, right? So in order to avoid chemical equilibrium, the key ingredient is that we need reaction rates to be small. Small with respect to the Hubble expansion rate, right? And in order to have a small interaction rate, we could have like two options. Either we have small couplings. If we have a UV complete theory, you can take small couplings. Small couplings meaning typically 10 to the minus 10-ish or so. That's the idea. The order of magnitude that we need for couplings, 10 to the minus 10. 10 to the minus 10 is kind of unnaturally small. However, in particular models, it could be technically natural, right? In the sense of soft. That's one option that corresponds to the infrared freezing. So when you have a small reaction rate due to small couplings, small meaning 10 to the minus 10-ish or so. However, another option is to have ultraviolet freezing, and if you have like an effective field theory, you can have a reaction rate suppressed by a high scale. For instance, a high scale of the scale of new physics, or the mass of a very heavy mediator. That's another possibility in order to have this freezing. So, however, just remind you, so for WIMPs to happen, we need couplings, say order 1, electroweak couplings. For FIMs to be realized with much smaller couplings, 10 to the minus 10 or so. However, even such small couplings, 10 to the minus 10, are not guaranteed by no means in the universe. So we can imagine a theory, for instance, or a model where the typical renormalizable portals, so with dark matter, for instance, the Higgs portal, the neutrino portal, or the kinetic mixing are basically zero, right? So this will be like a nightmare scenario. However, that can happen. There's no guarantee that there are portals available for dark matter. So here's the question: what if dark matter only couples to the standard model via gravitational interactions? So as I'm telling you, this is like a nightmare scenario, and that's why I put these two frames here. And after all the proofs that we have of dark matter come from gravity. So this is a question that makes perfectly sense. Huh? So let's put ourselves in the scenario where dark matter only couples to the standard model via gravitational interaction. So the question is, how could we produce it in the early universe? Okay, so no worries. Dark matter is unavoidable produced by a number of gravitational processes. And that's what we study here. How to produce a dark matter out of the gravity. So the first idea is to have a connection between dark matter and black holes, and in particular, primordial black holes. So we don't want here the black holes to be the dark matter. I mean, if black holes are long-lived enough, they will contribute for the dark matter budget. However, here we will assume that the black hole will completely evaporate, so that they will not be the dark matter. We want another particle to be the dark matter. So, okay, now black holes in a nutshell. So they could be produced in the early universe via a number of processes. I will not focus here on how these black holes, this population of black holes was produced in the early universe. We just assume that they were there, right? So for instance, they could have produced via density fluctuation, via large density fluctuations that can collapse in primordial black holes in the early universe. But the point that once they're produced, we know basically what will be their evolution. So they will lose mass by emitting all particles via Hawking operation. At first approximation, they will have a spectrum, which is basically a black body spectrum, with a temperature, which is the inverse of its mass. So its mass will start to decrease because they will evaporate via Hawking radiation. That means that their mass decreases and the temperature increases, right? So black holes will unavoidable radiate all particles, all standard model particles, but also all states in the dark sector. And in particular, the primordial black holes will unavoidable radiate dark matter.
So,
yes?
Particles would be then dark. I mean, it would be dark matter, but it would be also Hawking radiation. I mean, that's what they're saying, that this
exactly that black holes will radiate dark matter via Hawking radiation. Yes. Well, they will meet all standard model particles. So dark matter as well. If you have right-handed neutrinos or whatever, gravitons, inflatons, everything will be radiated by black holes. Yes. And in particular, dark matter. That's the focus of discussion here. But this completely, I mean, all that I will say, I mean, yes. So I will focus here on dark matter. But for instance, if you're interested in leptogenesis, we could basically trade all what I'm saying by a right-handed neutrino that will decay with a CP violating phase, blah, blah, and generate baryogenesis via leptogenesis. So at this point, it's very general. So primordial black holes will unavoidable radiate every single particle, no matter how heavy it is via this Hawking radiation. Yes. Yeah, sorry, I forgot to say, please interrupt me at any point if you have any question or comment. We'll see that the typical mass of black hole. Yes.
Nicolás, yes.
Yeah.
The particles that are radiated by the black hole are only the ones that are, say, lighter than the temperatures, right?
Yes, yes, exactly. Yes, that's right. However, we will assume that the black holes will fully evaporate. So at the end, their mass will be zero. So I mean, they will be testing.
Yes.
They will have temperatures super high. So at some point, they will radiate. Yes, sorry, I forgot to say that.
Yes.
Dark matter, no matter how heavy it is, provided that black holes fully evaporate. Yes.
Right.
But I will emphasize that point later on. Thanks, Claudia. Yes, so we see that the typical masses of the black hole that we will care here correspond to small masses. So black holes lighter than 10 few tons. That means that they will fully evaporate before the onset of BDN, and they're poorly constrained. We'll talk about the constraints of such a light black hole. So at the end, we'll have like an effective theory with three parameters that characterize the black hole. So one would be the mass at the moment of formation, right? Or if they are produced via the gravitational collapse, they will be the initial mass could be traded by the initial temperature of the standard model at the moment of formation. So the initial mass, the initial spin of the black hole. And one comment here is that for the sake of simplicity, I will assume monochromatic black holes, so that all black holes will have exactly the same mass and exactly the same spin. That, of course, that may not be the case, but this could be generalized to other distributions of masses and spin. Okay, that's for a single black hole. However, of course, we don't want a single black hole. We want a collection of black holes. And the amount of black holes will be characterized by this parameter beta, which actually corresponds to the ratio of the initial black hole energy density normalized by the initial standard model energy density. So beta is not a constant parameter, because the energy density of black holes and the energy density of standard model scale differently. So beta will increase with time. Okay, so here, for instance, just to give a taste of what we're doing. So we're showing you the typical Boston equation that one has to solve for the evolution of the mass of the black hole as a function of the time out of the spin. So A star for me is the dimensional spin parameter. So just to show you that black holes, so for a maximally rotating black hole, so a K black hole, so they have that, just to show you that they have like an explosive evaporation. So the bulk of the energy is released at the very end of the life of the black hole. So we have a dramatic decrease at the very end, both for the mass and for the spin parameter. Yes, just to have you, or you to have an idea. So now, how dark matter is produced? So if you want to compute the dark matter density, it's kind of simple. So what you have to have is the density of black holes and see how many dark matter particles are emitted per black hole. So the dark matter density is basically the PBH density times the number of dark matter particles emitted per black hole. And the number of dark matter emitted per black hole is, as Claudia said, so it will depend on whether the dark matter is lighter or heavier than the initial black hole temperature. If it's lighter, so if the dark matter mass is lighter than the initial black hole temperature, it will produce all along the evolution of the black hole. However, if the dark matter is heavy, it will just be produced at the very latest stage of the evolution of the black hole when the temperature is higher than the dark matter mass. Another thing I want to emphasize is that as the energy density of black holes scale like non-relativistic matter, they can eventually dominate the total energy density of the universe, giving rise to a non-standard expansion rate of the universe, so a non-standard cosmology. Yes, so we could
but
have,
this doesn't contradict the usual cosmology. At what stage is this supposed to happen at the beginning of the universe?
yes, we want all this to happen before BBN. And then we are super free with the expansion rate. Yes, of course, at BBN, you want the universe to be radiation dominated.
Yeah, right.
Standard model dominated. But before you're free. So I will put this constraint, I think it's in next slide. So exactly, yes. So
Yeah,
here
okay.
I'm showing you a typical parameter space. So I'm showing you here the typical masses of the black hole in grams. So we want black holes to have masses of grams, kilos, or tons. So very light black holes. Why so light? Because I want them to fully evaporate before BBN. Yes. So they're black holes that need, say, seconds, maximum seconds, just to evaporate before BBN. So I want it to be very heavy because of BBN constraints. I don't want them to be very light because very light black holes correspond to black holes produced very early in the universe. And we have constraints coming from the scale of inflation. So CMB here means the inflationary scale. So the normal observation of tensor modes, right? And this dotted line corresponds to two regimes. If above the dotted line correspond to scenarios where PBH eventually dominate the total energy of the universe before BBN. And below the dotted line is always radiation domination. Another thing is this greenish parameter space here, this chunk of the parameter space, I put GW, correspond to a parameter space where I have problems with gravitational waves. So these gravitational waves will mess up with BBN. So I want to avoid these three regions, CMB, gravitational waves, and BBN. And now here I'm showing you these four lines correspond to the parameter space required in order to produce the whole dark matter abundance, where all the dark matter is produced via Hawking radiation for 4 different masses. So this solid line corresponds to 10 to the 15 GeVs, this one to 10 to the 9 GeVs, the dashed dotted 10 to the 3 GeVs, and the dotted line to 10 to minus 3 GeV, so 1 MeV. So we can see different slopes. For instance, in this part, what is vertical is when the universe is dominated at some point by black holes. And these two slopes here, for instance, this one and this one correspond to two regimes, dark matter heavier and lighter than the initial black hole temperature. In this, if beta, remember, is the amount of black holes, initial amount of black holes, is very small, we will not be able to produce the whole dark matter abundance. And also in this parameter space, like bluish, I set constraint from hot dark matter if dark matter is lighter than 30 GeVs or so. This is exactly Lyman alpha. I want dark matter to be cold. So if in order to avoid conflict with Lyman alpha observations, I want to avoid this chunk of the parameter space if dark matter is lighter than 30 GeVs or so. Yes, okay, so just to emphasize, so with primordial black holes, just to take into account the Hawking operation, I know how to produce the whole dark matter abundance for dark matter heavier than, say, 30 GeVs or so, and as heavy as the Planck mass base. Yes, okay, are there questions or comments at this point?
Yeah, well, I am confused by the fact that you're producing, yes, dark matter. I mean, because the black hole is supposed to be just for what, I mean, for what form from also dark matter at the very beginning. I mean, what, I don't understand.
No, okay, yeah, okay, it's true. I'm assuming that initially there's no dark matter whatsoever, and all the dark matter is produced by Hawking radiation out of this primordial black hole.
But why? Why is it produced only dark matter? I mean, an amount of dark matter by Hawking radiation.
Why?
Why is dark matter produced that way? I mean, it's not the usual dark matter.
No, I mean, there's no like coupling to play with. You cannot switch off this dark matter production. I mean, it's not that black holes are producing every single particle, and I'm assuming here that the particle content is a standard model plus dark matter. So black holes are producing every single particle, I mean, democratically, and in particular dark matter as well. But and there's no I mean, there's no free coupling. The only coupling here, if you want, is the Planck mass, the Planck scale. But here I cannot. I have no freedom here at all. Okay, the only freedom I have is the spin of the black hole. So for this plot, I did some. I'm assuming this is Schwarzschild, so there's no spin at all. However, later on I will show you some, and this is analytical. So I can show you some numerical plots, like 100% numerical, where I'm taking into account the spin as well. So I'm exploring the Kerr regime. But yes, at this point, there's no freedom at all because it's purely gravitational process. So I cannot, yes, there's no freedom. So the only free parameter is of course, the dark matter mass and the characteristic of the black hole. So mass of the black hole and spin parameter. And how many dark black holes do you have there? But that's it. Huh?
May I have a question, please?
Sure, please.
Madam Smetana is speaking. I understand that you produce dark matter, but at the same time, the black hole will produce also the other particles, right?
Yes.
And my feeling is that the lighter is the particle, the more abundance it gets by
yes.
evaporation.
Uh-huh.
And my question now is, do you check if you don't overproduce, for instance, photons or other particles, neutrinos? Like overproduction of other particles when you want to achieve the abundance of dark matter.
Yes, there's no problem with that because everything here, I mean, the typical constraint will be, okay, so once black holes evaporate, they will produce, if you want, they will overproduce these particles, but they will very fast, they will thermalize, right? And you want that the temperature after this thermalization is is bigger than few MEVs because you want all this to happen before BDN. So, but that's true. So you're producing dark matter, but also all the other particles. So you're injecting a lot of entropy. So I don't have plots of the temperature evolution of the universe, but of course, if the black holes dominate the total energy budget of the universe, you can have like a non-trivial behavior of the standard model temperature, and that's of course that has to be taken into account, that we indeed took that into account. Yes, so actually in all these parameter space here, when I say PBH domination, in all these parts here, you have a non-trivial evolution of the standard model temperature, and I think that's what we were calling overproducing the standard model. But at these such high temperatures, all the standard model very fast thermalizes. So if the final temperature after the evolution is bigger than few MEVs, so bigger than the BDN, you're perfectly fine. Yes, but that's a good point. Thanks. Yes.
May I ask a question?
Yes. Okay.
So about the mechanism of primordial black hole production. You said, if I'm not wrong, that they are produced from the collapse of the fluctuations in CMB, right?
Mm-hmm.
And what is the rate? What is the mechanism of this collapse? And in particular, about the spin of the black hole.
About the what, sorry?
Spin.
The spin, you say? Yes.
Yeah. So then they should be produced from the fluctuations. What kind of tensor, or what? Can you comment about first of all, the rate and then the spin?
Yes. It's true that, I mean, that would be like completely a different talk because I mean, how primordial black holes are produced. I mean, it's I mean, we have ideas how they are produced in the early universe, even if it could be in a matter dominated universe on radiation domination. But of course, and you can compute that if you have like the full model of inflation, of reheating, blah blah. However, here I want to avoid such a discussion. That's why I focus on like an effective approach. So I just assume that we have this population of black holes with a given mass and a given spin.
Okay.
Yes, but of course that's something that we could and maybe we should do is to put this in the context of an inflationary scenario with a reheating scenario, right? And see exactly what is the prediction for this black hole, for the masses, for the spin, and of course you don't expect them to be monochromatic. You expect them to have like a mass distribution. Yeah.
Let me ask a simple question. Sorry, are you assuming that this dark matter particles couple more strongly to gravity than the usual matter?
No, it's gravity, exactly GR.
Okay, thanks.
No, thank you.
And maybe one more question.
Sure, please.
Did you investigate whether there is some difference of the evolution or the production if you take into account the dark matter to be boson or fermion? Is there something different?
Yes. There are a small difference here. Obviously, it's a boson. If it's a fermion, there will be a small difference, but it's really order 1. But yes, so actually we have a code. So the plot I will present you corresponds to different work. So the first one, so these ones that I are showing are really analytical, but at the very end you will see the same plot, but using this code that solves exactly the Boltzmann equations, taking into account the gray factors, the spins, everything, and you will see some difference, but they're very, very small. So at this point, the main message is that it's independent of the spin. However, there are small differences. Yes, and at the end, I think I have a plot. Well, maybe not for different spins of the particle, but different spins of the black hole. That's for sure. Yeah, but they are different, but very small. Yeah, but yeah, thanks. Okay, so I think at this point, just to summarize a bit, I assuming that dark matter has only gravitational interaction with the standard model, and the dark matter was produced. I mean, if black holes are there and if they have a mass of grams, kilos, or tons, they could produce the whole dark matter abundance observed. However, I was assuming another thing, and I didn't tell you, is that I told you that I assumed that between the dark matter, between the dark sector, the visible sector, we have only gravitational interactions. However, I also assumed something about self-interactions, so interactions within the dark sector. So I assume that basically have no self-interactions. Now we'll see what happens, how this scenario is modified when I allow dark matter to have sizable self-interactions. So when I'm talking about self-interaction, I'm thinking really about, for instance, if that's a scalar, I can have quartic interaction, or if it's a boson, if it's a non-abelian boson, I can have quartic and trilinear interactions as well. So for instance, if dark matter has this quartic interaction, for instance, just for the example, dark matter could thermalize, meaning that it could reach kinetic equilibrium via elastic scattering. But they could also have inelastic scattering. So for instance, this 4 to 2, right? I'm just assuming a quartic coupling, right? Here is quartic, 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 and quartic. So it can have elastic scattering, and then dark matter could reach kinetic equilibrium. So dark matter could thermalize. And it could also have number changing interactions, so inelastic interactions. And this dark matter could reach chemical equilibrium, right? So we'll assume that dark matter will explore what the effect of such processes. So in that case, if we want to compute what's the dark matter abundance, the questions are different. So what's the total energy transfer from the black hole to dark matter? What is the dark matter temperature? Because the dark sector could reach equilibrium, chemical thermal equilibrium. So that's true if dark matter reaches kinetic equilibrium. And what is the dark matter equilibrium number density if chemical equilibrium in the dark sector is reached. And we'll see that this self-interaction will have a strong impact on the dark matter behavior. For instance, it will increase the dark matter number density. If I have, for instance, these 2 to 4 interactions that I showed you before, these 2 to 4. And also it will decrease the mean dark matter kinetic energy. And this is very simple to understand because I could have interactions, for instance, 2 to 4. And there I'm trading kinetic energy into mass. So I will increase the dark matter number density, and the price to pay, I will decrease the mean dark matter kinetic energy. And these 2 aspects are kind of nice for us. So here I'm showing exactly the same parameter space I showed you before, beta, and the dark and the black hole mass, right? So this dotted line corresponds exactly to the flow to the line that I showed you before. So the scenario without self-interaction. And now this solid black line corresponds to the case where I have maximal self-interaction. So it's a model independent result just based on conservation of entropy, conservation of energy. So for instance, if you have a given model, a given particle physics model, I can guarantee that the line where that you have will be somewhere between these 2 lines. So somewhere in this gray region. So what we can see is that the dark matter production is more efficient, and therefore smaller values of beta could be explored, right? So for instance, we're exploring smaller values of beta, and also dark matter will cool down, and therefore KV dark matter will become viable. So this plot corresponds to a mass of 10 MeVs, but you can show you the same for different masses. So 10 kiloelectron volts, 10 GeVs, and 10 TeVs, right? For instance, in particular, in this case of 10 kiloelectron volts, it's possible to produce the whole dark matter abundance without being in conflict with Lyman alpha, which was the problem in the case without self-interaction. And again, just to emphasize this kind of model independent result, where you have only used arguments of conservation of energy and entropy density. Okay, so just to emphasize that self-interactions can have a strong impact on dark matter genesis via Hawking radiation. Okay, so I see that I'm super late, so I'll try to speed up a bit. So another point is gravitational UV freezing, another topic I want to tell you. And remember, so far I'm assuming that dark matter has only gravitational interaction. So I say one possibility is that dark matter is produced via black hole, primordial black hole, with or without self-interaction. That's a caveat. However, that's not the only purely gravitational process, because there's the UV freezing. But before that, let me just show you. So we have seen this plot on the left, right? I explained before. And here, the one on the right is exactly the same plot, just I'm changing the parameter space. So that's why I put an equal here. So these plots are exactly the same information, just with slightly different parameter space. For instance, here I'm showing you the mass of the black hole. Here and here I have the mass of the black hole. But instead of plotting beta, I'm plotting now the mass of the dark matter. So the information is the same. So I have here CMB and BBN. So CMB and BBN in red. In green, I have the underproduction. I have it here. And here I have the hot dark matter constraint. I have it hot dark matter constraint. So here, and I'm just showing you the same information on a slightly different parameter space, just to emphasize one point, is that if I want to produce the whole dark matter abundance, the typical parameter space that I need is this one, is the one here in white. So I typically need heavy dark matter, so 10 to the 6, 10 to the 10, 10 to the 14 GeVs, and very light black holes, so gramish or kilos, that correspond to very high temperatures. So if they were produced via gravitational collapse, that means that they were produced when the universe was super hot. So 10 to the 15, 10 to the 14, 10 to the 13 GeVs. So dark matter is efficiently produced via primordial black holes if dark matter is heavy and if the universe managed to reach very high temperatures. Okay. And I'm telling you all that because these conditions are also will also good for another dark matter production mechanism in the universe, which is the gravitational UV freezing. And what's that? So we can have the production of dark matter, so via collision of standard model particles, so E plus E minus, or whatever two standard model particle states you want to annihilate into dark matter. But however, here the mediator will be the graviton, so the massless standard model graviton. So this process you can always compute. They are typically very inefficient because it's gravitational production, right? But you, of course, you know how to compute that. After all, the graviton is a massless spin 2 that couples to matter via the stress energy tensor with a coupling which is the inverse of the Planck mass, right? So you can compute this kind of process at LAC or at any process. However, it's typically super subdominant. And why? It's because it's gravity, and gravity is weak. So these processes are typically very inefficient. However, there are regimes where this gravitational production, so this gravitational freezing, could be the dominant. And for instance, here I'm showing you a plot of the heating temperature of the universe and the mass. And here, this triangle, this gray triangle, corresponds to the dark matter production via gravity, via this gravitational UV freezing. So if you're on the edge of this triangle, you know how to produce the whole dark matter abundance. If you're inside, you're overproducing, and outside you're underproducing, right? And this will depend on the dark matter properties, meaning its mass and the dark matter spin, the reheating temperature, because it's a UV dominated process, and that's it. There are no free couplings because the only coupling is the Planck mass, which is fixed, right? And you can compute such an abundance, and will scale like this, will proportional to the mass times reheating temperature of the Planck mass power 3. So this is very inefficient because we have 3 suppressions of the Planck scale. However, this suppression could be overcome if you have large dark matter masses and large reheating temperatures. Okay? And here, just to emphasize that even if this gravitational process is very inefficient, this large suppression can be overcome by having heavy dark matter and high temperatures in the universe. Okay, so I think that now you see what we want to change the parameter space that I showed you before. It's just that this gravitational UV freezing and the dark matter production from primordial black holes are effective in the same bulk of the parameter space, meaning high temperatures and heavy dark matter. So here I'm putting everything in the same plot. So meaning the gravitational, the production via primordial black hole, which is all this white area, and this gray triangle, which corresponds to the UV freezing. So just to emphasize that the gravitational, that these two processes are efficient in basically the same chunk of the parameter space, and gravitational UV freezing strongly constrains super heavy dark matter radiated by primordial black holes. So this is in the case where the reheating where all black holes were produced at the reheating temperature. So at when dark matter, when the universe becomes radiation dominated, and these two plots here correspond to our fictional reheating temperature to 10 to the 16 or 10 to the 14 GeVs. So again, the message is the same. That if you want the dark matter to be produced via the Hawking radiation of primordial black holes, you have to be super careful because there are other production mechanisms there, in particular the gravitational UV freezing. Okay. Other questions or comments at this point? I'm super late, no? I think you expect me to finish basically right now, or do you have a couple of more minutes, Antonio?
You can continue, Nicolás, no problem. You can.
Okay. So I will be very fast in the last part. So other questions or comments at this point?
I am wondering, I guess I had a question. What is the I saw that in the dark blue and the green curve, both are the abundance below the upper limit, but what is the difference apart from that? Hot dark matter and the other warm dark matter, or in this explosion regions?
Here I'm showing you two colors. So the underproduction here is below this line. Oh, here's some, let me put this color.
Because I saw
below,
that in both there is underproduction.
Below this line, yes, these two, but the hot dark matter is a bit stronger in this case. So hot dark matter is below this line and underproduction below this line. But both are underproduction. The point that remember, this depends on if dark matter is heavier or lighter than the initial temperature of the black hole. So that's why you have two underproduction regions that correspond to the two limits. Dark matter lighter or heavier than the initial temperature of the black hole. Yeah.
Thank you, Nicolás.
But it's the same.
There were the first curve that you show. There were some that were the beta in the y-axis and the mass of the dark matter in the x-axis. You were having that the mass for lower masses of the dark matter, no, the other one, the first one, not this one, but the other one where there were no
this one?
No. Yes, the previous one, yes. That you were having some, no, the previous one. You were having some larger beta values for smaller masses. Yes. Why this different behavior when you go from, for example, 10 to the 1 TeV, or for example, below, let's say 1.
Okay.
Why this behavior of increasing and the other decreasing?
So here you have like one slope, whereas here I can have like two slopes. Is that your question?
Yes, exactly.
Why do you... Okay, so these slopes correspond to light dark matter, lighter than the initial temperature of the black hole. And here's heavy dark matter, heavier with respect to the initial temperature of the black hole. So for the dotted line, it's 1 MeV. So here, dark matter is always super light, so that it's always produced since the beginning of the evolution of the production of black holes. So here, dark matter is always produced. However, this dashed line corresponds 10 to the 9 GeVs, so it's heavy dark matter that can only be produced at the very latest stages of the black hole. That's why you have two different slopes. And these two different slopes correspond exactly to the point raised by Claudio, that dark matter or particles are always produced if their mass is smaller than the temperature of the black hole.
Thank you, Nicolás.
Point?
Yes, thank you.
So yes, I think I'm kind of late, so I'll be super fast in this part. The other is the idea of superradiance. So you can have superradiant production of dark matter by primordial black holes. So yes, I don't know how familiar are you with the superradiance. I will be very fast, so please stop me. So you can have superradiance also like in mechanical systems. So you can instance, okay, this is nothing to do with dark matter or black holes, just superradiance. So you can have, for instance, a scatter of a ball of a cylinder with a loose surface, and it will slow down, right? You have like a big velocity, it interacts, so they have friction, and after the scattering, you can have a small velocity. However, the picture can change if instead of that, you have a rotating cylinder. Yes, so you have a ball, exactly the same thing, mechanical system. Huh? A ball scattering off a rotating cylinder can increase the angular momentum and energy. And of course, this effect depends on whether you have dissipation or not, which is necessary to change the velocity. And this is very simple to picture. Huh? You have this rotating cylinder here, spinning fast. And if you have the scattering, you can have at the end a ball which increases the energy, right? Increases the velocity. So this super simple mechanical example could also happen with black holes. So with rotating black holes, we want Kerr black holes, not Schwarzschild black holes. So here will look like different, but the idea that waves that scatter off a rotating black hole, so again Kerr black holes, can increase in amplitude, not velocity, but in amplitude, by extracting angular momentum and energy of the black hole, right? So what we have to have is that angular velocity of the black hole horizon bigger than the angular velocity of the wave, right? So you have exactly an increase of the amplitude via this kind of scattering. However, this is very inefficient. It will be only increased by, say, a factor of a few percent, say typically 1% or so. So, however, we can have a superradiance instability if we manage this process to happen several times, not a single one. I don't want the increase of amplitude to be of the order 1%, but I want really an instability. And this could happen if we manage to trap this wave. For instance, we have this idea of black hole bomb, and the idea is to you put simply a mirror around the black hole, so that you can have multiple scatterings and the multiple increase of the amplitude. Of course, putting a mirror around the black hole is maybe not a good idea. We can have another way of trapping, and one is gravity, right? So if you have a massive particle, you have a gravitational barrier, and this could provide the trapping. And thus we will have superradiance instability, so high superradiance rate, if the Compton wavelength is comparable to the black hole radius of the black hole. And this is the idea of gravitational atoms. So we can form bounds, so bound states, so which is kind of typically called gravitational atoms. You can have like big clouds of dark matter or particles formed around the black hole. And I say that in order this to be very effective, we need the Compton wavelength to be comparable to the black hole radius. And I'm putting here the mass of the dark matter as a function of the mass of the black hole. And if you're on top of this line, this line corresponds to the parameter space where this superradiance instability is maximized. So there are several studies which focus on this chunk of the parameter space, which correspond to solar masses black hole, right? So like the one measured by gravitational waves. And so we can have effective superradiance if you have very heavy black holes with the masses of few solar masses and very light dark matter. So which could be like the axions typically, or axion-like particles. However, we study a different regime is where we have very light black holes, so of the gram scale, and again, kind of heavy dark matter of masses 10 to the 12, 10 to the 8. And remember that was exactly the parameter space that we have been studying so far. So here now showing you evolution of the black hole mass and spin in the case where without superradiance, which is the dotted line, right? Exactly the same plot that I showed you before. And now if we take into account superradiance, I show you what happens. So once the superradiance instability is reached, you have a big production of the dark matter abundance, right? You can see this like this very, very fast population of the dark matter, and the price to pay that you will extract a bit of mass, so few percent of the mass, but a big chunk of the spin. So we are extracting basically angular momentum, we're extracting spin, and we are producing a big population of dark matter via this superradiance instability. Okay, here I'm just showing
discontinuity. Why is there the discontinuity?
Yes, exactly. That's what I want to say. It's not actually. It seems like a discontinuity. However, it's not. It's just an exponential growth. So here in this small plot, I'm showing you like it's just a zoom. Huh? So you can see that it's not. It's really exponential growth, and the exponential growth is just the superradiance instability. So it's not like a step function, it's just a very fast growth, an exponential growth. Yes. And it's the extraction of angular momentum.
May I have a question here? I guess,
sure.
Like again, to standard model particles, I guess that such a superradiance will be also effective for other particles than dark matter. Is it true that it will be in other like stages, in other stages, right? So one should expect like stairway, no? Stairs, like each step would correspond to a given particle. Is it right?
Well, here we are typically at very high temperature. So before the electroweak phase transition, so all standard model particles are massless. Of course, they could have thermal masses, but yes, that's one point. How I have seen actually, I have seen there's another paper where they study superradiance with pions. So and black holes, which are not which are more massive than the one that I focus here. But yes, so it's possible to have this instability, superradiant instability with pions.
You are right that the standard model particles are super light in comparison with the dark matter which you assume here, right?
Yes, yes, exactly.
But if you have, for instance, type 1 seesaw mechanism for neutrinos, then the heavy orbital can be like also here present.
Yes, yes, you can have the same for you have a right-hand neutrino or any other particle. Yes, so this could be much more complicated. That I'm assuming that they have one more particle, so more plus one single particle. But of course, you have several ones. You could have like these stairs, as you say. Yes.
Yeah. Okay. Thanks.
Okay, and now super late. So here I'm showing you again the same parameter space. So beta and the mass of the black hole. And this line corresponds to the parameter space required in order to put the whole dark matter abundance for different masses. So green corresponds to 10 to the 15 GeVs, red 10 to the 12, blue 10 to the 9, and black 10 to the 6 GeVs. This is like okay, for a maximally rotating black hole, so basically one spin parameter, only when taking into account Hawking radiation. Now, if I take Hawking radiation and superradiance, I have not the dotted line, but the dashed line. So you can see that I have the instability in some points of the parameter space. And now the thick line corresponds when I take all the three processes I told you about. So Hawking radiation, superradiance, and UV freezing. Exactly for a maximally rotating Kerr black hole. And the same for different values of the spin parameter. So basically 1, 0.6, 0.3, and 0. And the difference between these 4 plots is basically superradiance. So here is maximal, so you can see like this dip here because of superradiance. And here when it's purely Schwarzschild, I don't have superradiance anymore. And here you have like intermediate regime. So this is like a summary plot where you can see the effect of these 3 gravitational contributions. And I'm super late, and I think, okay, I have another, I want to talk about light dark matter, but I'm way too late. So let me just show you the conclusion. So just to recap, so we could have these nightmare scenarios, nightmare for particle physics, that in the case where dark matter only features gravitational interactions. Is the worst scenario for us, particle physics, but I think after all, we have to keep in mind that the only probe that we have of dark matter comes from gravity. So that's the only interaction that we have for granted. And okay, so we can have primordial black holes formed in the early universe. And if they're lighter than say few tons, they fully evaporate before BBN. And therefore they're basically unconstrained. We have a lot of freedom when you study these primordial black holes. And these primordial black holes will Hawking radiate the whole dark matter abundance if the dark matter is in the range of the few MeVs up to basically to the Planck mass. So there are several caveats. For instance, one corresponds to the case where we have dark matter self-interactions, and the self-interaction will boost the dark matter density and will cool down dark matter as well, and therefore the KV parameter space will become viable again. So just to emphasize that this gravitational dark matter production is of course unavoidable. And if we take into account gravitational processes, we have to take all gravitational processes, right? So in particular, one is the gravitational UV freezing, which is effective for heavy dark matter and high within temperatures. And then we have to take into account PBH superradiance, which is effective for Kerr black holes when the Compton wavelength of the particle is of the order of the PBH radius. And just to emphasize that all gravitational channels have to be taken into account. And that's it. Thank you very much.
Thank you very much, Nicolás, for the very nice talk. Any question from the audience?
Yeah, I have a question. So, Nicolás, so you were assuming that the black holes, this primordial black hole, has more or less all of the same mass, right? You could have also, well, I mean, one would expect there could be a distribution of black holes, and there could be black holes which are actually very, very heavy, even to the point that they still remain, right? So in that case, you would have a component of the dark matter that is not formed by these extra particles, but by the primordial black holes themselves, right?
Yes, absolutely. Yes. So we, just for the sake of simplicity, we assume really monochromatic black holes, but they all have exactly the same mass. So we don't expect this conclusion to be effective if you assume like a kind of narrow distribution. But of course, if you have a very broad distribution, you could this will change, of course. So in particular, you can have some black holes that fully evaporate before the onset of BBN, but also some black holes that remain, and that will be a portion of the dark matter that we have observing. Yes, absolutely. But I mean, we need with all this machinery. I mean, we could redo everything just assuming a particular mass distribution function. Yes.
Okay, thank you. Very nice talk.
Thank you.
More questions from the audience?
And one thing, that's true for the mass, but for the spin. We're kind of lazy and we assume that the spin was a single one, right? But also we expect this to have a distribution function.
Okay, maybe I have another question. What Claudio asked now, I think this is something which can limit this primordial black hole scenario, right? That an observation of primordial black holes now would somehow limit the mass spectrum of primordial black hole, initial mass spectrum, right?
Mm-hmm.
And my question is another maybe constraints to the primordial black holes, and this is maybe only my ignorance, but how is it with a large scale structure if you have such black holes in this very early stages after inflation, I guess? So do they somehow interfere with the inflationary prediction of large scale structure?
No, not because remember, these are very light black holes that evaporate super fast. So their lifetime is 1 second.
But
and
okay,
so
but
they evaporate.
Maybe they can still, like, even within 1 second, they can produce some over densities, which later produce like galaxies and so on. Or no? Over
densities, but they fully evaporate. So at the end, I think if they are such over density, they will be completely diluted because the standard model reached again chemical equilibrium, so it thermalizes. So I think they will be erased.
Like, I'm thinking in the way that you know, at the end of inflation, the seeds for large scale structures were quantum fluctuation. So even smaller objects, right? And now you add to this soup, you add like a ton of massive black holes, which I guess will have an even stronger gravitational effect to some primordial clustering. So
yeah,
incorrect.
No, I think what you're saying is it's completely true. But it's true that we have to I mean, from CMB we know that the fluctuations are very small, right? So it's kind of isotrope, the
sure.
CMB. However, we need to have large inhomogeneities to produce them, the black holes, but they're very different scales. So no, it's true that producing black holes is kind of challenging because because of that, because you want from CMB you don't want to have large inhomogeneities. Yeah, this is.
Right.
But after the production of the full evaporation, I don't think. Yeah, I don't see any problem.
Okay.
Hmm.
Like my question is naive. I'm not expecting that.
Yeah, no, in structure formation, I don't have much. I'm not an expert in that, so maybe there are things to do. I don't know.
Okay, thank you. Very nice talk.
Thanks.
Thank you very much.
Thank you very much.
More questions? If not, we send.
I think Claudio has a question, no?
Yes, Claudio.
Marat had the raised hand. I don't know if he's still raising the hand.
Marat, yes,
Yeah.
please. And Claudio, please.
Yes. Can you hear me?
Yes, we can hear you, Marat.
Nicolás. Okay, thanks. Nicolás, I have a question to your slide number 27. You mentioned possibility to produce black hole in your scenarios and conditions of standard module particles. I wonder if you have some numerical estimates, what are the typical cross sections for this process?
You mean you want a number?
I mean, cross sections. Yes, approximately. What is order of magnitude? I understood you have a lot of uncertainties, but just order of magnitude. And just to understand if it's possible to measure this process either now or maybe in the future at accelerators.
No, forget that. No, I don't have a number, but this Planck suppression is just too big. So it's Planck suppression power 4. So
understand.
Planck mass minus 4. So it's typically, so you expect this to be S. Yes, so center of mass energy S over Planck mass power 4.
Understand.
This is yeah, this is super suppressed.
Understand. Okay, thank you.
Thanks for the question. Claudio, no?
Yes. Well, yeah, this is some just some thought I had. So if you start with primordial black holes, which are formed by these large fluctuations, then you end up with say like a soup of non-relativistic matter there, and then these black holes evaporate, and of course they evaporate into relativistic particles. So you're changing from non-relativistic to a highly relativistic gas. So would that make any effect, say maybe just flattening out later fluctuations or something? I'm just trying to...
No, it's through the scenario that you're referring to. Yes, if beta is big enough, you at some point the universe could be dominated by black holes. So you have a non-relativistic, like a non-standard expansion era, so dominated by black holes. But I think if they evaporate early enough, so much before BBN, I don't think there are major problems with that. Huh?
Right. Okay.
Because yes, you evaporate into highly relativistic particles that thermalize very fast.
Right.
So I think there's no. I mean, the point is that we have no observation before BBN, right? So we are super free.
Right. Okay. Thank you.
More questions? If not, we thank Nicolás Bernal again for the very nice talk. We meet in the next seminar. Thanks a lot, Nicolás, for the very nice talk.
Thank you.
Goodbye. A nice afternoon, all of you. Bye.